Okay, thanks everybody for coming. I realise everybody's dying to go home, so I'm hoping this will be, I don't think I'll use the whole time, but then you never know with these things. Hoping this will be an entertaining guide to Shor's algorithm, if I can get the clicker the right way around. Let's see. Oh yeah, here we go. So, who am I? I'm James. I've worked for ThoughtWorks for the last 4 years. I'm about to leave ThoughtWorks. I'm starting to work for a company called Codurance on July the 8th. You may have seen Sandro Mancuso doing a talk 2 days ago, or yesterday, in fact, here. So I'm going to work with Sandro in a couple of weeks. I still love ThoughtWorks. If you're interested in ThoughtWorks, by all means, reach out to me. I've got 2 more weeks. It's been the best experience of my life. And here's some of the books that ThoughtWorks people have written down the years. Now, I love Krakoff. Who here's from Krakoff? I'm not. A few people, yeah. I've been to Krakoff twice before. I love the buildings in Krakoff. Earlier on, I did a talk about architecture, and I love the Krakoff architecture. I love that old square. You get those all over Europe. You don't really get them in the UK, I think, because the UK was bombed to shit in the war. And you get these horses in Krakoff city centre. I was here with my wife last year in October, and we were wondering why there wasn't any horse poo lying around on all the streets, because there's so many of these horses. And then we noticed one of the drivers might have been the guy in that picture poking the horse in the bum with something. It turned out he had a big net, like a fishing net, and he was catching. I don't know how they know that the horse is about to do that, but maybe they left their tail or something, who knows. And I had a bit of misfortune. I had an eye infection over the weekend, which has got worse. So I was on this medication, and it was a bad plan. I went for a run around the River Vistula. If you turn your head on the side, that looks a bit like a songbird, by the way, one of those birds with a long thing. I didn't feel great. I did a talk on Monday, and then in the evening I was out with these guys. They're speakers at this conference, and unfortunately it didn't end all that well to me, and I've got a bit of a black eye today, but you can pretend you didn't see that. So, what am I actually going to talk about? Right. I'm hoping everybody in the room understands cryptography to an extent, but I'll go through a quick 101, and then we'll talk about some quantum computation and why it's important right now. So, Cryptography 101, I'm going to kick off with a quiz. Does anybody know who these 3 chaps are? Nobody. Normally I get a guess at this point, but it's wrong. That's their names. If anybody's ever heard of these people, good luck to you. Anybody want to guess who these 2 are? They're a bit more famous than the last 3. Anybody? Okay, so these 2 are Diffie and Hellman, that are quite important in the cryptography world. Now, these 3 are probably the most famous in cryptography. Anybody want to guess at what they are? They are RSA, indeed. Rivest, Shamir, and Edelman. I'm going to come back to those gentlemen later. I apologize for the lack of diversity on those 3 slides. Many middle-aged looking white men like me. So, Crypt 101. What's cryptography all about? So, essentially, Alice is trying to send a message to Bob, and Eve is trying to listen to that message. That's all cryptography is about. Now, crucially these days, Eve is trying to listen to the message in such a way that they don't know she was listening. That kind of always was the case. I mean, I know when I read about Enigma in the Second World War, the Western powers decrypted most of the German messages, but we didn't want them to know that we were decrypting their stuff, so we had to make a judgment as to whether we acted on that intelligence or not, and apparently that was always the trade-off going on. So, how does cryptography work? Well, there's my colleague, Fu, representing the hacker. Essentially, you've got to find something that's easy to do in one direction and hard to do in the other direction. RSA relies on the fact that it's easy to generate a large number from 2 prime numbers, but it's hard to work out what the 2 factors of that prime number are. In fact, it's exponentially hard, and we'll come back to that. And there's discrete logs and elliptic curve do something similar mathematically that's easy to do in one direction and hard to do in the other. Earlier on, I saw Simon Maple, this was just a couple of hours ago, doing a talk on live hacking, which I thought was great. But one thing he missed out on, and this is nothing to do with this talk, but I had some spare capacity, was I have this talk where I talk about how to do the green glow on people that you see in films. Because one moment when he was doing his hacking, he said, "Oh, I need that green glow. Don't know how to do it." Well, I'll show you. We did this shot at work. That's from a couple of slides ago, and see, Fu's got that green glow on him. That sets him out as an evil hacker type person. And we wanted this for a joke in our newsletter. So how did we make this shot? Well, it's an MVP. It's a quick, cheap shot MVP, and that's how we did it. So, moving on. Anybody in this room used quantum computers at all? Or programmed them? No? Nobody at all. Well, I'm glad I decided to leave this section in then. Quantum Computing 101. First of all, classical computers. We all use classical computers in this room, right? They essentially work with gates, logic gates and bits. In a classical computer, you plus bits through logic gates. The bits are either zeros and ones, and they go through a gate, and you might get an output that is not a 0 or a 1. Well, something, a different combination of zeros and ones. That thing up there on the left, that is an OR gate. You can see that if A or B is closed, it lights up. That's actually implementing an OR gate. So A and B are representing the bits, and that's the OR gate. This more complex picture that we've got here, I forget what these shapes mean. Some of them are OR gates, some of them are not, and AND gates, I forget exactly. But this is a schematic drawing of how a classical computer does 16-bit floating point arithmetic. So you've got all the input bits at the top, it goes through all those gates, and then out the side comes the answer. That's how floating point arithmetic works. Now essentially, that is all classical computers do. They take those zeros and ones, they push them through gates, they get a different answer. And everything that we do as programmers is abstractions built on top of those logic gates. Now, in a quantum computer, there's something called a Qbit. I'm not going to spend too much time on this, but essentially what that means is it still returns a 0 or a 1 if you measure it. But before you measure it, it's kind of holding both values. It's holding both values, usually with weighted probability that it's going to return one or other of the values. So, but as soon as you observe the value, it will give you a 0 or 1. And it will continue to give you a 0 or 1 every time you subsequently read it. What that's called is collapsing of the quantum state. Up until that point, it has a value in a 4-dimensional vector space. Believe me, you don't need to know the maths. It can be represented like this. That's a qubit. The arrow indicated by psi there, effectively, the closer it is to the top, the more likely it is to give you a 0 when you measure it. Okay? But if it's anywhere other than pointing straight up or straight down, that qubit has both values at that time. And you can use both those values in any computation, and that's where the power of quantum computers comes from. It's really wacky, I know. I'm glad I don't have time to explain it properly. Quantum computers have logic gates the same as classical computers, except these work on the quantum state. So similar to classical computers, they can do like 180-degree transforms, they can do 90-degree transforms, they can do all sorts of things. But as I say, if the end result is a quantum state which isn't exactly 0 or exactly 1, you're holding both values, and you can use both values. If you're interested, I don't think I've got it on this deck, but those gates there, those representations, those are from IBM-Q. If you Google for IBM-Q, you can get a free account. They have 2 publicly available, 3 publicly available now, quantum computers. You can submit your own programs to them. They're not very powerful, but they're there. They'll help you to learn how to program. So I'm going to talk a bit about superposition and interference. Now, first of all, I'm going to do a quick... Oh, that's the wrong one. I wanted to come to... Hang on, that's the fella. Mirror displays. Here we go. Bear with me, I always get this wrong. I wish I could do this smoothly. The 3 of us have been trying to reproduce the double slit experiment. So this is Ben, this is James, and I'm James as well. We've used equipment that you can find anywhere. Well, 3D printer maybe. Yep. Wow, down here we made a frame and a holder for our double slit. We made the double slit by using a sharp knife in between some tin foil. Here we have a laser pointer. It's the same laser pointer that I'm going to be using during the presentation. So who knows, I might even reproduce it if I've got this equipment, but it'll probably end up in the bin later. Down this end, we've got 3D models of Ben. We've got Big Ben and medium-sized Ben. Little Ben we left on the table over there somewhere. And they're holding our screen to receive the results. So let's see if we can make a diffraction, an interference pattern at the other end of this desk. It's very scientifically done this, and there it is. Can we see the interference pattern? And that is quantum physics in action, as demonstrated for you in the ThoughtWorks office. Thank you very much. Okay.
Well, that was perfect for a second.
Oh, yeah, we get a really good shot of it. Always get the outtakes. Okay, so we can see the interference pattern there. It's strongest in the middle, and then it has dark bands and bright bands going out. So why have I shown you that? Well, yeah, I need to clear that thing away, don't I? Go away, you. Just come over that way. That's probably better, isn't it? Because I don't know how to get it to move. Right. So, Jung devised that experiment in 1809, I think, and he wanted to demonstrate that light traveled in waves. Up until that point, the prevailing theory had been that light travels in particles. It was a theory put forward by Isaac Newton, Sir Isaac Newton. He called them corpuscles, and nobody had challenged that theory, or nobody had found a way to challenge it. I think it had been challenged, but nobody had found a proof. So what Jung devised was an interference pattern. So what he reasoned was, if I can get these things to interfere, then obviously they're waves. And this is essentially what he did. You can see that you get positive interference, you get negative interference. You can reproduce this thing in a water tank with standing waves. It'll look something like that. So light travels as waves, right? Well, quantum mechanics then came along in the 20th century, and it turns out that no, light doesn't travel in waves. Turns out it travels in individual particles called photons. Now, those photons have no mass, but they have momentum. I can't get my head around that. I'm not a quantum physicist. The further away you are from a light source, it isn't that the wave is spreading out and weakening. You see photons less frequently. Okay? So what's going on with that interference pattern? Well, what everybody said at the start of the 20th century was, well, they're obviously interfering with each other. They have wave-particle duality. And everybody believed that for a while. But then, later on, it turned out if you can get, and this has happened, you can fire one photon at a time through those double slits, right? So there is nothing there for that photon to interfere with, and then you detect them on your photon detector. One at a time, they're landing on that photon detector. This is a simulation, obviously. But you can see that the interference pattern still builds up. And there is nothing physically there for that photon to interfere with, and yet it is somehow interfering with itself. This is where superposition comes in. Because what is happening in that is that with a different probability, the photon is actually going through one or other of those slits, but it's going through both at the same time. Now, according to the many worlds interpretation, on which quantum computers rely, and what I'm going to show you relies on the many worlds interpretation, those photons are going through both slits. And the interference pattern is this photon in our universe that we can see is interfering with all the other possible paths that it could have taken. That's an interference pattern. So just to illustrate superposition, I promised my daughter I'd keep this slide in, although it's not strictly necessary. That's my daughter's cat. That's Clementine's cat. Of course, she has the standard mood that all cats have, which is indifference. We ran a superposition experiment on the cat to see if it could hold more than one mood at the same time. So we used 3 qubits to do the transform on the cat. Turns out it can have different moods at the same time. I'm always worried that joke won't work in a language that isn't English. So why do I show you all this? Well, in quantum computing, and I'll show you a use of it shortly, there is something called the quantum Fourier transform. It is not possible to observe all of the calculations that your quantum computer is doing. But if you transform the register upon which transformations are taking place, using the quantum Fourier transform, or other transforms do exist, I just don't understand them, what you can then start to do is not look at all the other calculations, but look at the interference patterns that are being set up between those calculations. So that's where the power of the quantum computer comes by. By harnessing the interference patterns between your simultaneous calculations, you can gain insights as to how those calculations are working, what's going on in the many worlds. It's far, far too complex for me to drill down into that exactly, but I can show you a real example now. So, I always used to call this the elephant in the many quantum rooms. When I've talked about what quantum computers are going to be useful for, Shor's algorithm is kind of the elephant in the room. Does that phrase work in other languages? Yeah, good, thank you. I always forget I shouldn't use an English idiom. Mind you, I kind of forced to there because of the title on the slide. Yeah, let's pretend it's in Polish. So, the elephant in the many quantum rooms is Shor's algorithm. And now this is a method for factorizing numbers. So we already know that RSA relies on the fact that factorizing numbers is hard. So how does Shor's algorithm work? Well, this seems random. It is random. This is counterintuitive. Let's say I'm trying to factorize a big number. Firstly, pick any random number less than that big number, right? You don't go through and measure all the primes and see if they work. That takes too long. That takes more than exponential time. If it happens to be a divisor, great, you finished, you were lucky. Obviously, that's vanishingly unlikely. Now, this is the crucial part. You need to find the period of that number, a, with respect to n. We're trying to factorize n, and we're trying to find the period of a to the power x. So what that means is say a is 2, a is 2, a squared is 4, a cubed is 8, and so on. Keep raising that number to a power, but always take it mod n, because you should know from your modular mathematics that what that means is the period of it will be a maximum of n. Okay? So it'll have a period less than n. And I've got an example that will demystify this for you in a moment. Now, with some simple linear algebra, if it's an even number, if the period is even, then step 6 is rather some simple mathematics. It tells us that a to the half of that period plus 1 and a to the half of that period minus 1 will give us the factors of the number. And I'll show you with a simple example. Don't try to get your heads around that too much, but by all means take a photo of the links. So here's an example. Say I'm factorizing 15. Well, we all know it's 3 times 5, so that's pretty trivial. I'm going to choose a random number less than 15. In this example, I've chosen 2. So the greatest common divisor of 2 and 15 is 1, so I haven't accidentally found a factor, so I carry on. Now, I find the period of 2 mod 15. So 2 squared is 4, 2 cubed is 8, 2 to the power 4 is 16, which is 1 mod 15. So if I keep raising it to successive powers, it goes 1, 2, 4, 8, 1, 2, 4, 8, and so on. So the period of 2 mod 15 is 4. Right? So what does that tell me? It tells me that 2 squared, because half of 4 is 2. So 2 squared minus 1 is a factor, or a multiple of a factor. In this case, it is a factor. And 2 squared plus 1 will give us the other factor. And I think we all agree that 3 and 5 are the factors of 15. Now, that sounds fairly simple when I write it like that, right? But actually, it's far from simple. And what I wanted to do was understand myself how complex this is. So, when I was on my way to work one day, and if you work in London like I do, you'll understand this, you spend a lot of time on trains getting very bored. So, I wanted to do this. I wanted to understand exactly how. Is that big enough? Do I need to make that bigger? Okay, so I chose a big number. Oh, wait a minute. Don't do that. Command plus should make it slightly bigger, shouldn't it? Anyway, it doesn't matter what these numbers are. So 1,517. I chose a number that was the product of 2 largish primes. Okay? I randomly chose a number less than it, and I happened to choose 4. And as you can see, I'm doing 4 squared, 4 cubed, and so on, and so on, and so on. And then you can see I'm taking it modulo 1,517 in this column here. No, sorry, in this column here, in modulo 1,517. So that number there never goes bigger than 1,517. Lower down, we'll see it eventually gets to 1, and that gives the period. So I'll scroll down and down and down and down and down. There it is. So the period of 4 with respect to 1,517 is 90. Okay, so what does that tell us? It tells us that 4 to the power 45 plus 1 and 4 to the power 45 minus 1 will give us the factors of 1,517. Great, so I scroll up in my spreadsheet and I see, oh, damn it, it overflowed at 25, so I need to do pure integer arithmetic, so this is no good to me. So then I spent the rest of the train journey and some of the morning trying to find a number that was small enough. There you go, there's one. 16 has a period of 45. I'm like, oh, damn, 45 is no good because it's not an even number. So that number can't help me. So I come through. Next, I tried 5. By this time, you can see I've added column F to make it easier for me to just by eye find it. And its period is 180. That's no good. So eventually, I go through 10. I remember being excited by because I got to 10. And I found, yay, look, its period is really low. Oh, damn it, that's an odd number as well. So that was no good. And eventually, 14 was the number I was looking for this demonstration. Because if we go down here, we see that 14, the period of 14 is only 24. I say only 24. But crucially, 14 to the power 12 does not overflow in Google Sheets. Now, I warn you, if you ever want to give this demonstration in any conference, don't download your Google Sheets to Excel and demonstrate it in Excel, because Excel overflows earlier. And if you look at the video that I did at Lead Dev London, you see me going, what the hell just happened? That didn't overflow this morning. It's because they told me to download it into Excel because the Wi-Fi was crap. So let's get back to our slides. Here they are. Is that my slides? Yeah. God, I can't read it. So here's the slightly more complex example worked through in the numbers. Oh, God. Go away. What if I click on that? Will that help? There. All right. So factorizing 1,517. We randomly choose a number. We choose 10. I've missed out some steps here, obviously. We go through. It's an odd number. No good. So then we choose 14. OK. The period is 24. So I'm going to do 14 to the 12 plus 1 and 14 to the 12 minus 1. There's 14 to the 12 minus 1, and you see it's that big number there. But the greatest common divisor of that and 1,517 is 37. By the way, you use the Euclidean algorithm to do that last bit of the calculation. That's trivial in terms of complexity. And the other big number, 14 to the 12 plus 1, gives us 41. So, hey, presto, we factorized 1,517. It was hard work. We saw that, right? So what's the point of Shor's algorithm? Well, it is this. Step number 4. The steps I just showed you in the spreadsheet, you can imagine, are really, really complex. You saw the size of those numbers, and that is a tiny, tiny number, 1,517. In order to find the period of a number on a classical computer using an algorithm similar to what I had in that spreadsheet, that is of exponential complexity. Okay, so that doesn't help. That hasn't made it any simpler. It's more efficient than checking every prime number, but it's still of I think it's sub-exponential complexity. So it really doesn't help. Now, I saw this written down, and I'll probably misquote it, but I'm told that the biggest possible computer that's available now will take about 80 years to factorize a 2048-bit key. So that's pretty safe, and that's what most RSA algorithms are using. Some people say we should be using 3072-bit keys. And I saw this written down, I saw it in a presentation, that if you could build a theoretical classical computer using every single electron in the universe as a bit for computation, that computer would take longer than the lifetime of the universe to factorize a 3072-bit key using classical computation. However, we don't care what those intermediate results were in that spreadsheet. They are totally irrelevant to us. So we don't need to do every single one of those calculations. We only care about the period. So what if there was a way that we could simultaneously raise 14 to every power less than 1,517 and just examine the interference pattern between all of those results such that we could yield the period? And that's exactly what Shor's algorithm does, and that's exactly what the quantum Fourier transform is used for. And when you use that methodology, you have reduced it from being an exponential complexity function to a polynomial complexity function. So anybody in this room should know what that means. It means that it's vulnerable. Is that my computer just receiving an email or something? Apologies. So I'm going to show you a quick demonstration now. And I hate it when I do live code demos because they never work. Now, if you're interested in playing with quantum code, there's a few ways. The way that I've found most pleasing is I use Q#. Microsoft has produced something called the Quantum Development Kit, and it's got a language called Q# with which you can write quantum programs. So I decided I wanted to implement the quantum, that algorithm, basically. And I went into the Microsoft libraries, and I looked at everything, and they already had an implementation, but I didn't like the Microsoft implementation. Somehow Microsoft manages to, the code quality is not great in its own implementations, unfortunately. I have said this to the people who wrote these libraries, so I'm not speaking out of turn. Just some real basics here. I'm going to show you, this is a Q# program. Now, Q# is the quantum programming language, but you have to have a classical computer driving your quantum computer. So in the case of the Microsoft languages, obviously it's written in C#. I know it's a Java conference. If you shut your eyes, it'll just look like Java. You can pretend it's Java. So in here, I have something called factorizer, which is straightforward, old-fashioned C# code. It's supported by tests, and everything in that algorithm we did, it's only step 4 that requires a quantum computation. Steps 1, 2, 3, half of step 4, step 5, and 6, you can do on a classical computer. There's no point in sending stuff into your quantum computer that you can efficiently do on a classical computer. That just doesn't make sense. So what I've implemented here is basically a strict separation of the classical parts from the quantum parts. So if we look down here, you can see it's doing this, for example, modular exponent helper, get greatest common divisor. So get greatest common divisor, there's a very efficient algorithm that you can implement in a classical computer. So if we just look in there, you'll see there's all this code here that does the non-quantum parts. We don't have time to go through it all, but it's available on GitHub. I think the slide that I was just showing has my GitHub link. And it comes through, and I wrote this, I finished writing this, I started writing it about a week or 2 weeks before I was talking in a conference in Ukraine last year, and I finished writing it about an hour before the talk, which was all a bit hairy for me. And then when I ran it, it ran successfully, and I went, yeah! And then I ran it again, and it crashed my computer, and then I ran it again, and it crashed my computer, and eventually I managed to get it to run on about the 8th attempt. I did a screen capture, which is what I showed you on that last slide, and then I just sort of stuck my thumb in the air and went, okay, I don't need to know why this didn't work. However, I know now, if I do .NET run, is that big enough? Can people see? It's not that interesting what it outputs. I advise, if you're at all interested, have a look at the code. It's .NET, you know, so I'm not using the .NET equivalent of Graal VM. Sorry, Chris Tallinger. So whatever that is, so it took a while. So we're factorizing 15. Oh, and we randomly chose 10. So we got lucky because 10 is a multiple of 5. So that just gives us the right answer. I'm going to run it again. Factorizing 15. This time it's chosen 2 as the random number. Now it's using the quantum algorithm, using the quantum Fourier transform. It's taking ages. You can see how long it's taking. This is because classical computers cannot efficiently simulate the quantum Fourier transform. There it goes. So the output is now telling us that, okay, so it got half the answer. It's trying it again. This is a complex bit that I didn't bother explaining. Sometimes the quantum Fourier transform, especially if you use the fast Fourier, which I don't have time to explain, and there you go, now it's crashed. Didn't expect that, to be honest. It's been a long time since it crashed on me. So what I did was I took this program up to Manchester to one of my colleagues, and I'll show you his implementation very quickly in a moment. And I told him it crashed randomly, and he looked at it, and about 5 minutes later he said, well, I found the bug. I fixed it. He obviously didn't find all the bugs. Let's see if it works for 13 now. If it doesn't, I'm going to run Andrew's program, because his works all the time. So I was up in Manchester working for ThoughtWorks, and I had this grad, Andrew. He was on the beach, as we call it. I think other consultants call it the bench. Hey, what have we got? Estimated divisor is 4. So there you go. So what it's done is it's done 13 squared plus 1 and 13 squared minus 1. So I happen to know that 13 squared is 169. Is that right? Does that make sense? Yeah, so 169 plus 1 is 170. That gives you the 5. And 169 minus 1 is 168. And that is a multiple of 3. So that gives you the 3. So yeah, it worked there. We found the factors as 5 and 3. Not that interesting to look at, I grant you. Now, let's come over here. And I said to Andrew, I would like to see you actually implement the quantum Fourier transform, because the Microsoft implementation I didn't like. I didn't understand it, basically. So Andrew did that. His code, I think he copied my classical code, but then implemented the quantum code. So you can go online and find how to implement the quantum Fourier transform. If you come into Andrew's GitHub, which is on the next slide, you'll see it there. By all means, download it, have a look, because that's a proper implementation of the quantum Fourier transform. Oops. Let's do .NET Run and see what this does. I think it's going to try and factorize 15, or at least it did yesterday when I did it. And what happened? It said the factors of 15 are 3 and 4. 3 and 5, that's more like it. So again, somehow it chose 13. So it got to 13 squared, which is 169, add the 1, deduct the 1. So that is Shor's algorithm. And by all means, go to GitHub, download those implementations, and have fun with them. And then that comes back again. So there's our GitHubs. If you want the nice unit tests and the classical bits, go to my GitHub. If you want the I'm a grad and I know how to do stuff without that stuff, then go to Andrew's GitHub. And there's Andrew messaging me, telling me that his algorithm took 1.5 hours to factorize 35. So it doesn't seem that useful yet, does it? So is RSA dead? So it will you need 3 times the number of qubits as there are bits in the key. So to factorize a 2048-bit key, you need about a 6,000 qubit quantum computer to run Shor's algorithm. The biggest computer we know about is about 72 qubits, Rigetti in the States. I think there are bigger ones now. This slide's a little bit out of date. But my point is that it's a long way off. So what should we do if RSA is dead? Well, there's something called BB84, which I'm going to demonstrate the concept of in a moment. And there are classical algorithms that are 100% provably quantum safe. Here's some examples. And there's a project, Open Quantum Safe, which has been running since 2016. So let's talk now about post-quantum cryptography. Now, I decided that I wasn't going to demonstrate this, even though Andrew wrote the code in Java, because I thought it's too late to show complex stuff. There's something called ring learning with errors. I thought I had it on the, oh no, it's on the next slide. Essentially, instead of using a single number to hold the key for your cipher, it uses a polynomial over a finite field. Okay, so essentially, it's blowing out the complexity. It's putting it's just really complex. So the hard part, again, is recovering the private key from the public key. The keys are very big. And unfortunately, and this is my understanding as to why nobody's using it, there is a performance penalty. So nobody wants to put this type of cipher into their browser now or into their public channel. Please, by all means, have a look at that. That's Andrew's implementation, his Java implementation. And down below, there's a very interesting page there on NIST, which is the American thing, the National Institute for something, in which there's a really good write-up of what post-quantum cryptography looks like. So, is anybody familiar with Amazon packaging? Did I do this in Poland, where you buy something off Amazon and it comes in a box like this big and it's like something like that? So that's what happened to me there. Now, I have another quick film to show you, if I could find my mouse pointer. There it is. I'm hoping it's that. Yep. And here we go. Oh, no, you're not seeing that.
We're going?
Yeah, we're going.
Right, I'm James. Today, we're going to do another...
I forgot to stop the presentation. Escape, please. Thank you. It was all going far too smoothly, wasn't it? Let's start again. This time I didn't have my ThoughtWorks colleagues to help me, as you'll see.
We're going?
Yeah, we're going.
Right, I'm James. Today, we're going to do another quantum experiment. This time, we're going to talk about the polarization of light photons. Here, we've got my daughter Felicity, and here, we've got my daughter Clementine. Okay, and outside, what have we got? We've got the cat.
It's definitely very helpful.
That is Clementine's cat, and as you can see, she wants to get inside. Girls, does one of you want to empty this box out just to show Amazon's packaging? And what was it they sent us through the post? Well, it was these 3 tiny pieces of polarizing light filter. Okay, now, let's run our experiment. Girls, if you take one, Clementine, take another. So you take those. Take them over to the window. Okay, so now the girls have got the 3 light filters. Clementine's got 2, and Felicity's got 1. Okay, so now Clementine, if you hold 1 light filter up to the light, that's it, that's good. Now, hold it so that it's facing right towards me. So it's flat towards me, that's good. Okay, now, bring the other light filter up, Clementine. And that's it. Now, they're at right angles to each other, and you can see that where they overlap, no light is getting through. If you just rotate it around again, so it's the other way around, Clem, you can see that when they're in the same orientation, it still lets half the light through. So now, if you put them together the other way around, that's it, hold them tightly against one another, that's it. No light is getting through. One of the filters is stopping all the light, the other filter's stopping the other, the rest of the light. Now, Felicity, get the other filter and hold it in front, so it's touching. You can see still nothing's coming through the 2 filters that are touching. And on the back, please. Okay, still nothing comes through the two filters. Now, slip it in between the two filters. That's it, brilliant. Now twist it towards you, and make sure they're tight at the top. Hold it there. Fantastic. Now you can see what's happening. Where there's one filter, some of the light stopped. Where there's three filters, some of the light stopped. Where there's only two filters, all of the light is stopped.
Okay, so what's going on? How does introducing a third filter let more light through? That seems entirely counterintuitive. Well, this is the first time I've tried this explanation, so I hope it works. Although I did test it on my wife, who knows nothing about physics, so hopefully it's clear. There's that last picture. Where there's one filter, 50% of the light is stopping. Where there's two filters, 100% of the light stops. Where there's three filters, oddly, not all the light stops. Somewhere between 50% and 100% of the light is stopped. So what is possibly going on? Well, light moves in random polarizations. Now, this is the key point. When you go through a polarizing light filter, not only does it stop some of the light, if in this representation here, you can imagine all the photons that are perfectly vertical in their orientation, their polarization, they'll all go through. All the ones that aren't vertical, well, all the ones that are horizontal will get stopped, 100% of those. All the ones that are in between, which is obviously going to be most of them, the closer they are to the vertical, the more likely they are to get through. But all the ones that get let through get disturbed and are now in the vertical polarization. So we lose half the photons, but we no longer have randomly polarized light. So if I then put the second filter at right angles to the first, it stops all the light, because every single photon is polarized exactly vertically. So what happens when I introduce the third filter, right? So there's the same picture there, one filter. And you can see I've got the vertical filter on the left, and I've got the horizontal filter on the right. So now if I introduce a filter which is at a 45-degree angle, and I apologize for the drawing, it was the best I could do on Google Slides. So because that is 45 degrees to those vertically polarized filters, 50% of them will get through. But hang on. That should say they're aligned at 45 degrees. And they are aligned at 45 degrees, except my picture's gone wrong in exporting it from Google Slides into, God damn. Should I show you the, no, just take my word for it. Oh dear. Let's come down here. Here's the original slide in Google Slides. So there's my 45-degree filter. Now, there you go. So it stops half of those photons, but it twists them round to a 45-degree angle, right? So now when it comes to the final filter, which is aligned horizontally, some of them get through. So by introducing a third filter, we've let more light through. Now, why is that important? Because you can use these filters to behave as photon detectors, similar sort of technology. But the problem is, as soon as you read the alignment of a photon, you risk changing it. And that is why BB84 is provably secure, because observing the quantum state may change the quantum state. Okay? So how does BB84 work? Well, there's an explanation on that wiki page there. First of all, Alice and Bob are going to agree. Alice is going to send the key using polarized light. She'll either send photons like that or diagonally. So you can see if she's using the horizontal basis, she sends a photon like that. If she wants to send a 0, she sends it like that. If she wants to send a 1. Okay? Then Alice sends Bob the key, and Bob doesn't know what basis she sent each of those bits in, so he randomly chooses the horizontal basis or the diagonal basis to measure the bits. So far, so good. So there's the random basis, there's the random bit, and then Alice sends that. Bob chooses a basis at random, and he might measure something different. So why is that useful? Well, because then they have a public discussion about what the basis was used in each stage. So Alice tells Bob, I used plus in these places and the diagonal in these other places. So I used horizontal in those places and diagonal in the other places. Bob says to her, okay, this is where I use plus, this is where I use diagonal. And you can see where they agreed. He, 100% of the time, he measures the correct value for the bit. Where they disagreed, he might have got the correct value, he might not. So what do? You just get rid of the ones that might be wrong. And everything that's left becomes. This is a one-time use key, okay? You only use this key for the single message. You have to make sure the key is longer than the message you're sending, but it is 100% secure because of that, provided that what you use to generate the random bits is a true random number generator. Don't know how you do that, by the way. So why is it secure? Well, because Eve didn't know what basis the key was going to be sent in. That's one thing. So she's got no way of knowing what the zeros and ones were. She only knows. Alice says out publicly, right, this is the basis I used on each point, but that means Eve can only recover at most 50% of the key. Or in fact, it's even less. I can't remember the maths. And furthermore, if Eve was eavesdropping, Alice and Bob know, because they can compare a subset of the generated key, and if Eve was eavesdropping, that introduces errors in the key. So simply, it's slightly more complex than that, but you're welcome to go and read it, but essentially, they know whether it's been eavesdropped. So great, if it's been eavesdropped, you send the key again. You carry on sending the key until it's not eavesdropped, then you send your message. 100% secure. There are known quantum key distribution networks. At the moment, the first Bennett and Brassard demonstration back in 1984, I believe, used fiber optic cable over a distance of 2 meters. So not exactly that useful. But here are some of the networks that exist. And as I understand it, the Chinese network, because I saw a talk on this a few months ago, uses a satellite to beam up some photons somehow up there and then get the result back. Don't quite understand the hardware myself, but there are people in the world that do. So it is being used, but it's obviously very expensive. So, post-quantum cryptography is there. It can be used, and I advise you to use it. Why? So I'm going to finish with a brief history lesson. So, we're back to these middle-aged white gentlemen. In 1976, Diffie and Hellman published their paper on symmetric key exchange, I think the paper was called. No, it's called multi-user cryptographic techniques. There you go. I think it was a demonstration of a symmetric key exchange. So 1976, that's when the thing was invented. 1977, Ravesh, Shamir, and Aderman published the RSA algorithm, and I believe they patented it as well. So RSA's been in existence since 1977. But who were those 3 gentlemen that nobody's ever heard of? Well, in 1997, the British government announced that those 3 cryptographers, Cox, Williamson, and Clifford, had devised something that eerily similar to RSA some years earlier. I don't know how long earlier it was. It's some years earlier. And of course, they didn't tell the world, because that was an official secret. Now, right now, every government in the world is spending a lot of money on quantum computers. We don't know how much, but we know they are doing so. Now, if you're sending messages encrypted in RSA, they are 100% safe today. There is no doubt about that, provided your key is long enough. But no one's using RSA 129, right? So that's fine. But do you want that message to be still secure 5 years from now or 10 years from now? Because I guarantee you, all of the world's governments, all of the world's secret services are storing all of the RSA exchange traffic. They're doing that right now because they know that at some point in the future, they will have quantum computers strong enough to break that RSA cipher and to read those messages. So if you care about your stuff being secure, not just today, but 5 years, 10 years, 15 years from now, you should already be transitioning to those post-quantum cryptographic methods. Thank you very much.